Okay, by my clock, it's time to begin. So let's do that. Whoever's in the back, would you close the door? Thank you. So, as with all IETF sessions, we begin with the note well. These are your rights, privileges, and responsibilities. Make sure that you are aware of what they are before you contribute. Second, please make sure you treat each other well. It's okay to disagree with an idea. It is not okay to attack the person with the idea. Meeting tips. Everybody in the room here should have be using the on-site tool. We need this to manage the queue. We're going to augment the note-taking that Kirshner has agreed to do with some of the things from the script and from the Eckerbot. So let's make sure that you're using the queue management so we know who's speaking when. Off-site people, of course, need to use the full Meetico in order to see what's going on here in the room. The agenda and slides are at the URL here. The notepad, which is used for the note-taking, is at the next link. Please jump in there and help Kirshner. If he spells your name wrong, fix it for him. If he summarizes what you said wrong, fix that too. All right. Zulip is the chat.
May I? The link are correct despite the title of the slides. Apologies.
Oh, right. We forgot to update the title of the slide here. But the links are correct. Audio stream will be available here at this URL, and then there are the two links for the Meetico session, the in the room link and the full. So, what did we get done since the last time? We've got a new RFC 9981 for the manifest number handling. We've got 3 documents in the RFC editor queue waiting for them to get enough time to turn them into the final form RFC. We've got a document with the ISG now regarding the server BCP, which they hopefully will get to IETF last call and AD comments shortly. And we've got documents related to ASPA in working group last call now. So hopefully those will be sorted out by the end of this week. Any questions on any of those? Okay, we have a very full agenda. So the agenda was posted to the mail list 2 weeks ago or so, and we had some discussion about that. And is there any agenda bashing before we get rolling through the agenda? Took 2 slides to put it up there. And then we get to the overflow things where we've got more requests than I am sure, have time. But it took 3 slides to put all of that. So we either need to be better about saying no to people who ask for slots or get more time. Time is of a premium here at the IETF. As you can see, there's already a lot going on in each session. I'm seeing no one get to the mic to bash the agenda. So we're going to go ahead and get going with that. So the first one is the ASPA stuff. I think Yob's going to talk about that. Did you get the new ones?
Yeah.
Okay.
Yes.
He's going to give you control as soon as he gets it up.
Testing 1, 2, 3. So is this the correct version of the slides? Because I uploaded 1 minute ago.
accepted the slides. Check if you changed anything.
All right, we'll see if it's the good version.
That is our intent.
Yeah. Okay. So this slot is sort of an open microphone session, I would say, to figure out, are there any outstanding issues that we identify and maybe can resolve immediately now, or are we good to go on publishing the ASPA cluster of documents? I'll give a bit of an overview of where we are, what the scope of the work is, progress report, and then it's open mic for anybody that has questions, comments, concerns, objections, approvals, tomatoes, whatnot. So ASPA is supposed to be the world's premier anti-route leak mechanism. We've been working on it for some time now. The original work started somewhere in 2018. As you can see, there was a little bit of a hiccup in the progression, I think mainly due to COVID changing the rules a little bit. But here we are. We're years of work and research have gone into this, and we're getting close to the end. So the current priority is to get a cluster of 3 documents published, specifically a document that stipulates the ASN1 profile on how you publish an ASPA into the global repositories, a separate document on how you can use this cryptographic attestation in BGP best path selection, that is the ASPA verification document, and then the third document is how do you transfer the validated ASPA payloads into the BGP routers so they can do the ASPA verification algorithm. These 3 documents are currently in working group last call. So this is a final opportunity for the working group to offer comments or suggestions or flag issues. We've not seen a lot of discussion or support on the mailing list. So if you are keeping notes on your to-do items, I implore on all of you, add to your to-do list to take a look at the ASPA documents and tell the working group what your thoughts are. Despite there not being a lot of feedback as of yet, what did happen, and for which I'm super grateful for the chairs kickstarting this a few weeks ago, is out of working group reviews materialized. So GenArt, BGP Directorate, ArtArt, these are review teams that exist outside of the SIDROPS working group, and they took a look at some of the ASPA documents and offered valuable feedback. So, like, one thing I found hilarious is that a reviewer noted as like a minor nit is like this instance of CA, you didn't capitalize the S. And then I was like, oh, that's so great, because we are using certification authorities, that's CAS, and we have customer AS, abbreviated to CAS. So we're using the abbreviation CAS for 2 things, different things. So I ended up changing the ASPA profile yesterday night to just fully write out certification authorities to avoid ambiguity. And this goes to show that having outsiders review these documents is incredibly helpful, because I mean, all of us have been staring at this document for a while, and none of us were like, oh, that is... and another reviewer pointed out, like, hey, the ASPA profile is missing a proper security consideration section, so that has been added now as well. Then let's talk a little bit about implementations. In the ASPA verification implementation section, a number of implementations are mentioned. This means we have the requirement of multiple implementations before RC publication properly covered. I cannot speak for the quality of these implementations. That is not my job. The goal of the implementation requirement in SIDROPS is to test the quality of the document and whether multiple groups of people, or AI these days, doesn't matter, can arrive at interoperable code and can read a specification and produce something. So there being 5 claims of implementation is good news. And this also means that as this technology matures and the commercial off-the-shelf vendors like Cisco and Juniper and Nokia and Arista and Huawei, when they take an interest in this technology, that they have open source implementations that they can test against and compare whether their work is doing the same as other implementations. So I'd say for SPA verification, we're in a pretty good spot. And that's good news. Then on the profile side, there's also really good news. There's multiple signers produced by multiple different organizations. Aaron, APNIC, and RIPE offer ASPA creation functionality in a very easy to access place. The open source package Krill has support for ASPA objects. There's a number of validators that have support for verifying and decoding these objects, and there's many objects in the global RPKI today. Again, this shows that there's from different angles, different groups of people looked at the same specification and arrived at results that are interoperable. So here I would say, cool, we did it. Good work, everyone. Yeah, we got the old slides. Oh no, I want the new slides. That's why they pay you the big bucks, man.
Yeah, the big bucks.
You get to be first in line for coffee and lunch.
Oh, yeah.
You just wave your chair badge.
Right.
No, old slides. It would be super funny if I uploaded the old slides and I'm now blaming you for showing the old slides.
Oh, no, that actually is the V2, but I find the bottom. Let's see. Still the old one.
Yeah.
Same ones.
I think it's like V2 at the end in the title.
Okay, it's this one. How do I move these upwards? Aha, maybe.
In Dutch, there's a saying, 3 keer is scheepsrecht. And that means that if you try something 3 times in a row, the 3rd time you'll succeed. And it's, yes, yes, yes. All right. So, Tom, where are you? Raise your hand.
Where is
He's in the back. It's the guy with the really nice haircut and the glasses. He's trying to look like me. Tom delivered us a pretty awesome thing. About 5 minutes before this meeting started, he finalized an implementation interoperability report for the RPKI to router draft. You can check the latest version if you click the word here in the slides that you should be able to download from the data tracker, but it's hosted on the SIDROPS wiki on wiki.ietf.org. And here is a partial screenshot to show you what you can expect. So what happened is that in a virtualized environment, multiple different server and client implementations were launched and fed the same data. and then comparisons were made, like, is the same thing, are they reacting the same way to the different events in the RPI2 router protocol finite state machine. So the long and short of this, and forgive me if I'm mischaracterizing the situation. If so, Tom, you need to come to the microphone. But I think with RTR, we're in a good spot, and there is sufficient interoperability among the different implementations to proceed with publication. But there are some minute differences. So some implementations have not yet incorporated the very latest changes to the draft, where 2 extra exit error reports were added. Adding those for most implementers should be very, very minor work, and it's on the exit path anyway. So yeah, in that sense, it's more of a nice to have than an absolute prerequisite to proceed. But one minor thing came up where I think there is some unclarity amongst implementers. And this is the case where if a client does a serial query to the server and the server returns a different different session ID than what the client had previously seen, in section 5.1 it says you do a full reset, the cache must be flushed, and you start a new session. And in 5.3, a slightly different reading is that the server instructs the client to do a full sync. Now, the ultimate outcome, whether you take the left path or the right path, is that a full synchronization happens. But in one case, you recycle the existing TCP session, and in the other case, there is a reconnect. And this discrepancy only came to light in what was it, less than 24 hours ago. So I think this is the one point in the RTR draft where we need to figure out what is it we want to be in the spec. But as I mentioned, the left or right, the client and server arrive at a synchronized state. It's just the number of steps between towards arriving at that synchronized state differs a little bit. So also for the chairs, this is the one issue that I'm aware of in RTR, and I think we should be able to hash it out this week. Yeah, and with that, we arrive at comments and whatnot. I know there are ASPA adjacent drafts existing in the data tracker, for instance, ASPA egress, ASPA slurm. And my advice to the working group would be, let us finish these 3 documents, and then after that is done, we can continue on the ASPA adjacent work. But we need the core specification out of the door before we take on more work. But yeah, are there questions so far, or feedback? Applause.
Finally came.
All right.
One bug to fix.
One bug to fix is the long story short, and please respond to the working group last call and help the chairs understand if there's consensus to publish this as RFCs. So thank you.
Are you still up?
Yeah.
Right.
Oh, there's Rudiger in the queue.
Hi. Just one question. The actual use of the ASPA in the wild seems to have resulted in some experience of well, okay, unexpected behavior, and that probably would be good to mention in the operational considerations section. Has anything been done in that area?
Yes, I have good news to report. The ASPA profile in its introduction states that operators, if they create an ASPA object, must list all their transit providers. And the ASPA verification draft mentions in the security considerations that if there's a partial listing, then some routes may be flagged as invalid. So both documents clearly express, if you create an ASPA object, list all your transit providers, not just some of them. And that should mitigate the issue at hand.
Do we have any advice on how to deal with transit providers that are not really invited and thus are not listed, and actually creating loss of connectivity as observed?
If you are peering with a network and you believe they are leaking your routes, you have to shut down the session with the leaker. That is the solution that is used for 20 plus years. You disconnect leakers. But this was not a leaker, this was a transit that was undocumented. So,
well, kind of.
Excuse me
so,
for skipping the queue. Job, please do not lie about what has happened.
Oh.
This was an undocumented transit which thought was transit and wasn't. Thank you. On behalf of CZNIC.
There is difference of opinion on what certain documentation means. But the point is, you have to list all your transits or disconnect from networks that are leaking your routes. That's all we can do. All right, next presentation.
There is another, yeah.
Hey, Job. Sorry, I'll keep it quick. So basically, with respect to the cache reset, right? Means you mentioned that the client is going to ask for a full update. So we don't have currently any threshold for which max number of cache reset that the client can be entertaining, because if we keep on entertaining the cache reset, it might lead to overwhelming of the connection, right? So do we intend to take this up to consider at max how many cache reset the client should be entertaining for setting the full reset to the cache server?
I had trouble hearing the question. Did one of you catch the question?
I didn't catch it. Can you repeat, please? Speak up a little
Sure.
bit.
Am I audible now? Is it better?
Or maybe you can type the question into the chat.
Yeah.
Did you hear the question, Jeff? Oh, Jeff, please relay the question.
Jeff is relaying the question. Thank you.
Yes, on behalf of Jishnu, who I work with, his question is basically about rate limit impacts of cache resets. If you get driven into a situation where you're doing resets often, the protocol is a bit ambiguous about the scenario and what each side should be doing about this sort of thing. Jishnu, did I get that right?
Yes, Jeff, absolutely. Sorry about my audio.
There currently are no considerations in relationship to rate limiting expensive queries. And I think this late in the game, it will be hard to come at a good outcome in a short period of time. So I think this is a good topic to explore in a new internet draft that, I don't know, rate limiting RTR, RRTR.
As two sentences that people move on. We did talk about this part of 8210 bis because the conversation, for example, that you and I had about what level of diff is a given server supposed to be able to cache on, and what happens if the server that's absorbing it as a client is running too slow. The protocol doesn't give enough hints about what happens when you can get behind, how much chance you have to get behind, and then what chance to catch up, or to suggest to the server hold on to stuff because you have a slow client. So I agree with you. The mechanism is clear in terms of what the protocol says, but as a development consideration, this is worth working on later.
Thank you for the question.
Thanks, Sherman. Happy to join in case you would like to take a new draft.
Yep, good to know.
You have to control.
All right, update on an entirely different topic, a mechanical aspect of the RPKI. How do we transfer those precious ROAS and ASPAs as fast as possible to you? Quick recap on why the ERIC synchronization project exists to begin with. We have rsync and RRDP at this point in time in the production environment, but there are some quirks with rsync. Rsync has a lot of state computation on the fly, so a client connects to the server, and then client and server jointly spend a lot of IOPS and CPU cycles to figure out what is the minimum difference to be transferred from server to client. So it's a little bit costly compared to static pre-computed content delivery. And more worrying, rsync has quite weak consistency guarantees. Because just because a certain information object has a particular file name with a particular last modified timestamp with a particular file size, it doesn't mean that that triple represents the same content as in the past or in the future. So you can end up in situations where you try and synchronize through rsync, but there is no transfer of updated data because the algorithm considers that there is no change despite there actually being a change. How can this happen? Imagine changing, for instance, the max length in a ROA, or in the same action, removing and adding a provider in an ASPA record. Then it could be that the resulting DIR encoding is of the same size as the previous version of the object, and if that's combined with say a timekeeping issue of sorts somewhere in the pipeline, you can end up with no propagation of information. Then in RRDP, there's a potential for retransmission of data. So for instance, an RP that had previously synchronized with rsync, if it then tries RRDP, it refetches the snapshot, and it's a refetch because in the cached, locally cached information, the client already has most of the data that is in the RRDP snapshot. And this is a result of the RRDP enveloping, the way the snapshots and deltas are packaged, don't offer the client insights into what is in that delta I am about to download. And the client can only learn what is in the delta until after they downloaded it. RDP does a full replication of the publication points history, but there's quite some churn in the RPKI. So this might mean that between the previous time that you synchronized and the next time, there are events that have been overtaken by later events, and you end up downloading information that is just no longer relevant. RDP is tricky to combine with rsync because of what I mentioned with the enveloping. So RDP doesn't exactly play nice with other means of transportation. And this, to some degree, means that RDP doesn't have the scaling properties I think we desire, because there's retransmissions, and the failure path is a bit costly because you fall back to a full snapshot download instead of something partial. Then both protocols have in common with each other that mirroring the data without explicit coordination is tricky. And what I mean with that is the publication point operator, they can choose to use, say, a CDN or a global anycasted approach, but clients cannot force the publication point to bring the data closer to them. So it is not possible to do permissionless mirroring of the data in the RDP and rsync architecture. And because of this lack of mirroring, not only can there be latencies and congestions, but there's also some degree of fragility because there is no redundancy. It's a full mesh. All the clients need to talk to all the publication points, and if they cannot reach one publication point because there is a localized transient connectivity problem, there is no other way to get to the same data. Now, Plan C, or ERIC synchronization, is an approach to address some of the downsides that I mentioned in the previous slide. It's a very different architecture than RDP and very different than rsync. It uses Merkle trees to structure and express to the client what the latest state is. And this way, the client can very easily identify and very cheaply, this is important as well, did something change? And if yes, what is it that changed? And then they can fetch just the difference. And they can do this without establishing a session of sorts where there is shared state between the client and the server, like there is with RDP. And it's static pre-computed content. So in this sense, ERIC is a bit more like RDP, where you can pre-calculate everything and serve static files to the client. So that is an appealing property. And it goes over HTTP, which is what most people like and prefer these days. So the deployment model is you have publication servers that use rsync or RDP. ERIC relays fetch in the data over those transports, and they repackage the data in a way that it's suitable for consumption by the relying parties, sorry. IETF in China was a fantastic inspiration for this protocol, because on paper, the ERIC protocol should be super performant and exceedingly well, like it's, you know, good job, Job. And here we were, Tom and I, hacking away at an ERIC implementation, and we discovered that it was not performing as well as we thought it would perform. And I think this is because the previous meeting network had some DPI component somewhere that in effect was a layer 7 rate limiter of sorts. Because what we discovered is that doing 100,000 plus HTTP requests is apparently too costly. And this was something that I did not really notice in Amsterdam on my high-speed connection. So what this taught us is that we need a way in the ERIC protocol to make it so that with fewer HTTP requests, you can get more data in one go. And the overhead per HTTP request is significant. So if you fetch a 2 kilobyte object, nowadays, a TLS session establishment can consume, say, 8 to 12 kilobytes. So you can see that there's an overhead of 4 to 6 times the actual payload that we're after. So it's really worthwhile to give multiple objects to a single request, even if that means that you give the client objects that they already had, because it's offset by the request overhead.
Job, less than 2 minutes. And
Slides.
Yeah.
So what we made is something called a write-ahead log, which is called segments in the ERIC protocol. Segments are an append-only aspect on the relay. The client can ask the relay, what is your write-ahead log from the last few hours? And then the client can cherry-pick which segments it wants to download to pre-fill its cache. And segments are nothing more than concatenated sequences of dir objects. An ERIC segment index is how you discover which segments exist. It's a very simple structure, and it's basically a sequence of timestamps and the latest indexed hash that is associated with the latest write to that wall log. And here is an example decoding. the ERIC index starts with a preamble about what FQDN is it about, what is the latest manifest this update contained in the segment, and then it contains a sequence of these tuples of the location of the segment and the hash of the index associated with the latest write to that segment. It's static data in the sense that only the latest segment is changed, and every few minutes the relay starts writing into a new segment, and that means the previous segments no longer change. Now, implementation efforts are underway. There's multiple projects happening at this point in time, and I hope that we can report to the working group soonish with some full end-to-end implementations of the relay and the client side, and invite more people to run measurements. And once we are confident that this system has the properties we want it to have, then maybe we can go for working group last call, but that's in a few months. Extra resources if you're interested in this topic, and apologies for overrunning by a few seconds. Thank you all.
Good afternoon, everyone. I'm Guo Zhen from China Telecom, and my presentation is, oh, sorry. Yeah. Thank you. And my presentation is IPv6 mapping prefix PDU for the RPKI router protocol, and Chongfeng is co-author. Okay, what about this draft? This draft defines a new payload PDU that carries a set of IPv4 prefix authorized by a single IPv6 mapping prefix. Its purpose is to carry MOA data from the RPKI cache to routers in IPv6 only environments. And why do we this now? Because at IETF 125 meeting, after draft IETF MOA profile was presented to record the working group last call, the chairs suggested that this PDU protocol extension should be delivered in parallel with MOA profile. So quick background, there are two supporting working group drafts. One is V6 Ops framework, and another is IDR Format 6 extension. So if you are interested about this, please read them via data tracker, and let me focus on MOA, mapping origin authorization. MOA is a side RPKI object defined in draft IETF MOA profile. It authorizes a IPv6 mapping fixed to originate mapping for one or more IPv4 prefix. The holder of IPv4 address block can authorize which IPv6 mapping prefix is allowed to map that block. Why does this matter? Because without validation, attackers can hijack IPv4 traffic by announcing fake mapping prefix. So here are PDU format and its key features. The PDU format follows the RFC 8210 structure, and the key features include multiple IPv4 prefix can be packaged into one PDU, and the flag field provides clear semantic for both announcement and withdrawal of mapping authorization. So here are the PDU generation and processing. On the catch side, PDU is derived from validate MOA object, and catch generate one or more PDUs per MOA, and IPv4 prefix must be presented in orderly. On the router side, when flags equals 1, routers install mapping authorization in the local MOV database, and when the flags equals 0, routers will remove the corresponding mapping authorization. For security consideration, the extension follows the RPKI and RPK router protocol security models. Routers must have a trust relationship with the cache, and the cache must validate MOA signature before generating PDUs. So we authors think the need is clear, and we would like to call for adoption, and comments are welcome. We will refine it based on feedback. Thank you.
Questions? Any concerns with the call for adoption? Okay.
Yeah, thank you.
Okay, hi, I'm Jia from Zhongguancun Laboratory, and I will present RPK-based validation with prioritized resource data. And now it is at version 2, and it's a joint work across Zhongguancun Laboratory, CERNET, Huawei, China Telecom, and Tsinghua University. So here's the starting point that operators already mix in non-RPK data in their routing decisions. SLARM, which is RFC 8416, already lets operators fold local assertions and filters into RPK validation. And operators may use local whitelists to avoid blackholing their customers, and they may use IR-derived or third-party fees where ROAs don't yet exist. So the data is already here, but when operators may have some low confidence data and they want to monitor its invalid results, once these data are folded into the SLAM generated VRPs, such invalid results cannot be distinguished from that caused by the ROA data. So the gap is there is no shared semantics. And today, each source is voted on ad hoc in vendor or operator-specific ways, and there is no consistent rule for who wins when sources disagree. And most of all, supplemental data can silently weaken RPKI with no one noticing. So this draft gives operators a common priority-aware way to combine the feeds they already rely on. And this draft rests on 3 principles. We separate what operators decide and what the framework guarantees. Firstly, the operators define the priority assignment. Operators define the priority tiers and which sources sit in which tier. And secondly, the framework guarantees the priority ordering, which follows a higher priority result must not be silently overridden by lower priority data. And thirdly, the operator defines the action per tier. Each tier maps to a local action, which is flexible to the operators. And this draft, in this draft, RPKI stays authoritative. The supplemental data must not silently override a validation result derived from the higher priority authoritative RPKI. And its default merge rule is highest priority wins. Where tiers disagree, the conflict is surfaced to the operator rather than resolved silently, which means the lower priority valid cannot quietly rescue an RPKI invalid. And here is an example, and we use 3 tiers and 3 different actions as an example. That operators may set the authoritative RPKI as a high priority, and its invalid results will be dropped. And the operators may also use the IR-derived feed and set with a medium priority and deprefer its invalid results. And they may also have some experimental data and with low priority, and they may only want to monitor its invalid results. So the point is the flexibility that operators freely map each source to a tier and each tier to an action. The same inputs can yield very different locally correct policies. Okay, as for the deployment, we propose 3 models, and I want to frame them as a cost ladder, not a rewrite. For example, the model A, it uses multiple caches and multiple tables, 1 validation table per priority with separate RTR sessions. Router differentiates via existing route policy, so it requires no RTR changes and no window code changes. And model B, routers pull per priority sessions and merge them into 1 table, and it also requires no RTR protocol change, only with a priority-aware ROV. And model C needs explicit metadata in RTR and with priority carried in band. It requires RTR extension and the router and RAM parties changes. The baseline model A requires 0 protocol and 0 window code changes. And we hear from Maria on the mailing list that BIRD already supports this today. And for model B and model C, they are optional and can be future work. And this is how the 3 deployment models actually work. That model A keeps multiple tables on the routers, and model B merges them into 1 table. And model C needs an RTR extension and carries per object priority in band. And this table presents exactly what each stakeholder actually has to touch. For Model A, it only requires configuration, so operators can start with Model A on today's stacks, BIRD or OpenBGPD, and Model B as priority-aware ROV, and only Model C touches the RTR protocol. And on the last Sunday's hackathon, we built an OpenBGPD prototype to realize these 3 deployment models, and we follow the 3 tiers of priority. And it is worth noting that in Model C, we use the per VRP priority in reserved batch of prefix PDU. And all 3 models worked correctly. And this table can show a good example of how the lower priority evidence cannot override a higher priority valid or invalid, just as a 3rd line that high priority invalid will cause the denied action. And although there is a medium valid action, the deny policy cannot be overridden. And also, as for the skill test, we ran the full ROA and with 250,000 local supplements and IR-derived data separately. And here are 2 takeaways. As the left chart shows, the Model A's configuration size grows to 16 megabytes with full ROA, while the Model B and Model C stays below 1 kilobyte. And secondly, as the right chart shows that as for the full ROA end-to-end validation time, which calculates from loading the inputs data to validating the routes on the routers, and the validation time stays similar, and the prioritized models have similar runtimes. So the semantics is richer, but there isn't significant additional validation overhead. And as for the outcomes, priority turns more data into differentiated action. And so now it is at version 2. And after the meeting at Shenzhen, we have done 3 key changes. Firstly, we explicitly clarify that RPCAS is authoritative, that this draft does not change global RPCAS authorization semantics. And second is priority safe semantics, that lower priority data must not silently override authoritative RPKI. And thirdly is that we change the mandatory RTR extension to a model A, B, C ladder. Okay, and to sum up, I want to use 3 words. The first is necessary, that operators already blend sources. We give it a shared RPKI safe semantics. And the second is safe, that authoritative RPKI is never silently overridden. And the third is affordable, that the baseline model A needs 0 protocol changes, and model A, B, C is an incremental ladder. And the draft and our demo are available on the GitHub, and we would welcome the working group's questions, feedbacks, and discussions. Thank you.
Thanks, John.
Joe Snyders. With the prioritization, I have some concern that inadvertently validation states are bleeding through into the routing data. Can you go back a few slides? There was a little bit back. Thank you. A little bit back. Yeah, sorry. Forward one again.
This page? Oh, no. This.
Next one, please. Next one. Yeah.
This.
This is the one. So the depref on IRR means that there is an implicit dependency on the existence of a ROA. And if the ROA is deleted, it causes the local preference in the network to change, which goes against the guidance in the recent draft, avoiding validation states in BGP that we approved as to be published as an RFC. So yeah, I think this is one concern. Prioritization of the information can result in churn if ROAS come into existence or flip out of existence, and I think that is a problem with the proposal at hand.
Okay, I want to clarify that this is just an example, and maybe the operators may have their own local supplemental data. They come from maybe their customers or their friends with other SPs or the AI info data, and they want to use it flexible. And I think this framework is to give them this flexibility. Okay, thank you, thank you.
Jeff Haas, I will be brief. I think this is a real problem. We have customers that make use of static configuration to override RPKI. I agree that we need a taxonomy about how we should be able to do that. I agree that information inside of RPKI router is helpful. So I support the draft. I think some of the contents we'll want to talk about, but I think this is good work to move forward.
Okay, thank you, thank you.
Okay, thank you. Let's move forward. Thank you.
Okay, can you hear me?
Yes.
Yeah, okay, so let's start it. Hello everyone, my name is Tomoki Yoshikawa from Kyoto University. And today I will present my work on post-quantum signatures for the RPKI. Since version 01 was submitted, the main release discussion has changed the direction of this work. So I will present both the results obtained so far and a proposal for how to organize the next documents. Next page, okay. This slide shows the current status of the draft. Version 00 was published on June 19th, and the current revision version 01 was published on July 1st. Today, I'm not asking the working group to accept all parts of 01 as a single specification. Instead, I will use 01 as a source of the current code and measurement results, and then ask how the work should be spread into separate documents. And here's a plan for this talk. I will first present the proposed document spread and then explain the main points that should guide the choice of post-quantum signatures for the RPKI. Yes, this slide shows my proposal to split the current work into 3 documents. The first would be an information document on PQC considerations for the RPKI, covering requirements, possible approaches, measurements, and operations without selecting a mandatory next seed. The second document would describe mixed certification chains as a migration method that is not tied to one specific algorithm. It would explain how an RPKI certification path can change algorithm at the CA boundary, and it updates the migration model defined in RFC 6916. The third document would eventually define a specific RPKI signature suite as standard Slack work after the base specifications, software support, and the needs for real use are ready. So these are proposed scopes rather than 3 complete drafts. So the first question for the working group is whether this spread is useful. And for the rest of this talk, I will mainly discuss materials that could go into the first document. The main idea is to study each approach against the specific needs of the RPKI, rather than starting with the winner chosen in advance. The study should cover pure post-quantum signatures, composite signatures, and related approaches such as a null scheme. It should consider both security and results from real implementations because repository growth, RP verification time, supporting signing systems and HSMs, and tests between different implementations can all affect the final choice. The purpose of this document would be to support related standards work, but not to select the mandatory next seed by itself. Okay. This slide explains the reason for this work and the scope I'm considering. NST has standardized post-quantum signature algorithms, and the pure MLDSA profiles for XOT 509 and CMS are now available. The base standards are therefore moving forward, while the deployed RPKI still relies on RSA 2048 with SHA 256. The main question is how to study and introduce new signature methods without changing parts of the RPKI that do not need to change. And this work covers signatures in resource certificates, CLLs, certification requests, signed object, and VZPSEC root certificates. It does not cover VZPSEC upgrade signatures, and it does not change RPL, TLLs, RRDP, RSync, RPKI payrolls, or router behavior. And this slide shows the main experimental case used in version 01. Version 01 used composite MLDSA 65 with ECDSA P256 as a difference point for testing and comparison. Both parts of the composite signature must pass validation, and for protection against forged signatures, the design aims to remain secure as long as at least one part remains secure. It also allows one RPKI object to carry one composite signature instead of publishing a classical version and a separate post-quantum version of the same object. There are, however, 2 important limits. And first, the pure MLDSA profiles for XOT 509 and CMS are now already RFCs, while the composite formats used in this experiment are still internet drafts. And second, an existing RP that supports only RSA cannot validate a composite object. For this reason, I think this profile is useful as an experimental reference point, but I am not proposing it as a mandatory next seed today. And this table are the composite result to my earlier RSA and the pure MLDSA measurements. I will focus on the highlighted MLDSA 65 plus P256 case, which signed 100,000 messages in about 41 seconds and verified them in about 11 seconds. RSA verification took about 1 second in the same test, so the cost on the RP side is an important point. The model repository size for the highlighted case is about 4 times the RSA baseline. Also, this is not a measurement of the complete RPKI repository. The point of this table is not to declare one row the winner, but to show that both repository growth and repeated RP verification need to be part of the selection process. The figure shows why the migration methods should be considered separately from the choice of signature algorithm. The parent CA remains on the current RSA suite and assigns the transition certificate using RSA, while the child CA public key inside that certificate use a new composite suite. An updated RP first validates transition certificate with the parent's RSA key, and then use the composite public key to validate the child CA and its object. The algorithm therefore changes at the CA boundary, which allows different subtree to move to the new suite at different times, while only one version of each subtree is published. The trade-off is that an old RP cannot validate the migrated subtree, so RP support must be ready before CA switch its subtree. This method is not tied to MS their DSA or composite signatures, and could also be used with other current and next suites. That is why I propose moving this design to a separate mixed certification chain draft. The figure and the main idea are based on Dirk's work. And this slide shows what I have completed and what still need to be done. The published code now covers draft 19 composite signature creation, validation, and performance tests, but it does not yet provide full RPKI object processing. The next step is to use composite signature in DR X.509 certificates, CLLs, and CMS signed objects, followed by full validation tests from CA to RP. At the same time, the current document should be split into clearer scopes, and the study should cover a wider set of signature approaches. The slide is my question for the working group. The most urgent question is whether the proposed 3 document split is the right direction. I'd also like to know whether any important requirements or selection points are missing, and which signature profiles or related approaches need more study. And I would welcome comments on any of these points. That concludes my presentation. Thank you to everyone who reviewed version 01 and joined the merit list discussion. Comments, implementation feedbacks, and co-authors are very welcome. Thank you.
So RFC 6489 talks about how to do algorithm transitions with RPKI CAs. And I think that you need to restructure this to align with the process described in that document.
Yes. Thank you.
Bob Beck, OpenSSL. I'm not a routing person, but I know slightly enough to be dangerous. When you go back to your little slide there where you were doing the transition from the RSA-CA, back. Yeah, there we go. Okay.
Yes, okay.
So you're aware here there is, of course, a downgrade problem.
Yes. It's a big problem, but basically
And by downgrade problem, I mean if RSA gets broken, the other thing doesn't matter because I can put my own MLDSA in there and I'm happy, and you'll trust it.
Yes. If we adopt composite signature, if RSA has is broken, we can
no.
use.
I'm not talking about composite versus non-composite. Pretend it doesn't matter. I'm talking about that RSA certificate on the left that's pure RSA that you are using to trust that transition certificate. It has signed over that transition certificate. So if RSA is broken, that's great. You've got a perfectly secure post-quantum algorithm in there, but you'll believe any key I give you because I can sign whatever I want.
Bob, I don't think the arrows are certificates.
I thought this was a trust chain. Oh, okay. This is not a trust chain. That's my misunderstanding. Okay. Because one part of your draft does say that you should not accept current suite and next suite for the same node in the tree to try to avoid the downgrade problem at one node in the tree. My concern there was that that's good, so I won't have a ROA misspecified on a downgrade. I can't hijack something there. But if other parts of the tree still accept this, I could have this ROA appear anywhere. So nothing's really safe until the entire tree does not accept this, correct?
Yes. Yeah. Thank you.
Okay, Tim Bruinzels, RIPE NCC, also responding to Ross, I guess. Yeah, so mixed trees or separate trees, because of the existing document for algorithm rollovers talks about having separate trees, a new tree where you do new things. I think that warrants a much longer discussion. We should probably take it to the list, but if you go down that route, there are quite a number of things that we need to touch in other spaces.
Correct.
Yes.
I agree with you, Tim, and that's why I want to have the discussion on the list. Okay. You can taste this. You're going to have to click this thing first. Now it works.
Okay, hi, Jia from Zhongguancun Laboratory, and this is ASPA-based ASPAS verification for BGP export, and it is now at version 5, and this is joint work across Zhongguancun Laboratory, Tsinghua University, CZ.NIC, NIST, and Huawei. And let me start with a quick recap. Our idea is simple, that is to apply the ASPA-based ASPAS verification to outbound eBGP updates. The existing working group draft ASPA verification verifies at ingress when a route is received. And this draft adds a check at egress on the outbound AS path just before export to a neighbor AS. And why would we verify at egress? Here are two motivations. The first is a partial deployment. In real world, some ingress routers don't yet support ASPA verification or BGP roles, while some egress routers may already do. So the egress verification then covers routes that would otherwise leave the AS with no ASPA-based export check. And the second is operational assurance. A route valid on ingress can turn invalid once exported. That may be because of the local misconfiguration, AS migration, or just omissions or mistakes in published ASPA records. And such errors might be subtle that may appear only on roads sent to one neighbor. And unlike origin errors, they seldom surface in public BGP analysis tools. So the egress verification is where we can catch them. As for how it works, the egress verification sees after the local AS prepending and before propagate to the specific eBGP neighbor. It verifies the exact AS path the neighbor will receive. And the verification chooses the algorithm based on the relationships. It matches what the ingress ASPA would apply had the route been received in the reverse direction. And the relation could come from BGP role capabilities, ASPA objects, or local configurations. If the two AS have a complex relationship, we can segregate the session into regular roles or decide per prefix, or operators may use the downstream algorithm to avoid false positives. And I want to make it very clear about the position of this egress draft. So it changes no ASPA semantics and disables nothing. It complements ingress ASPA. And if the OTC attribute is present, it must not be overridden by egress verification. So this draft acts as a local safety net at export. We can say that egress ASPA is to ASPA verification what RFC 8893, that RPK ROV at export, is to the ingress ROV. Okay, so what's new in this version 5? We've done 3 key changes. The first is we reposition the neighbor AS augmented verification, which I will discuss later. And the second is we expanded the optimizations. And third, we refined the motivation and the whole structure. As for the first change, neighbor AS augmented verification is to prepend the neighboring AS number to the path, which helps detect a missing provider AS in ASPA records. As shown in this table, which we analyzed before, that if there is an ASPA omission, which means one AS missing one of its provider in its ASPA records, such omission could be caught 1 or 2 hops away with existing verification. But with neighbor AS augmented verification, it can be caught locally And this is where the operators can actually fix it instead of 2 hops downstream away. And this mode most naturally used in the tight offline monitoring setups. Inline egress enforcement stays a local policy choice. And the second change is about making egress verification scale. We propose 3 approaches to optimize egress verification. The first is centralized or detached. The work can be offloaded to a route reflector or central node, or it can be fully detached via BMP, only notifications. And the second is deployment controls, with enable, disable, change enforcement mode as deployment evolves. And the third is partial verification. We can reuse the ingress verified prefix or verify only the local part with only full verification during AS merges, splits, or renumbering. And egress verification is deployable today on 2 independent open source stacks, BIRD and OpenBGPD. Egress verification is already available on BIRD that ASPA check can be called anywhere in the export filter on any path, including a prepended one. And also we implemented a demo on the OpenBGPD that reuses ingress verification and adds an outbound call set. And it supports direction aware, and it gives OTC precedence, and it can reevaluate the ASPA. It can reevaluate the route when there is an ASPA updates. Also, it supports 3 modes of monitor or enforce. So it is now at version 5, which includes all the planned revisions across the previous IETF meetings. And we wonder whether the design considerations are complete. Are there any cases, risks, or interactions we've missed? And we humbly welcome the working group's perspective of this draft. Thank you.
Alexander?
Hi, thank you for the presentation. I have some concerns about this document. It's not about the general idea, but some parts of the wording make me anxious. Especially the draft current version says that the egress ICE path verification should be performed on all roads possible illegal for being propagated at egress. I wonder what is possible illegal for being propagated. It is not specified in the document, and I'm not familiar with this term. It's not in the slides. It's in the draft.
I know. Oh, okay, and I will check.
So the draft uses term possible illegal for being propagated, and it's making me cautious.
Okay. As for the details of the draft, I will check it later carefully, and we can discuss.
Okay. And can you also get back, I think, to a few slides back, please? When you were discussing how to retrieve the local role. Yes.
This right?
Yeah. I'm confused that, with the second point, using ASP objects of local AS and neighbor AS. There was a reason why such technique was not suggested in ASP verification document. I think it should not be here too. So it's okay to use local role. It's okay to use some configuration. Using ASP objects for this purpose, I believe is unsafe.
Okay, thank you.
Jeff, as Alexander said about half of what I wanted to say, this slide is good. The consideration about local AS is very important. This is not well considered in the ASPA verification for import. The other case that should be discussed is remove private. So we're deleting private AS numbers.
Okay.
Thank you.
Thank you.
Okay. Okay.
Thank you. Thank you.
I'm Sriram from NIST. So this talk is about, so we have ASPA, which is already very well positioned, well thought through. The algorithm works well. So nothing changes about ASPA. I think Gia also tried to point out that with the egress verification also, nothing changes about the ASPA verification as we have it today. So that's something that we want to continue to progress and complete as we are doing currently. So once ASPA is available as the base, then we can think about some enhancements that may fill some gaps in ASPA. And the gap that I'm talking about here is not something that we haven't already acknowledged in the ASPA verification draft. We have acknowledged this, and here we are contemplating, okay, if there is, ASPA already moves the needle significantly in terms of detecting route leaks and a variety of path manipulations. But in addition to that, there is one little gap that I will describe in a moment. So we want to be able to see if we can have some solution to fill in that gap as well. So you'll see the details of that in a minute. So as I said, the ASPA-based AS path verification can detect all route leaks. It can also detect what we call forged origin and forged path segment hijacks. Those are well described in the ASPA verification draft. So it can defend against those as well when the update is received from a customer or a lateral peer. That's when we are doing the upstream verification. When we are doing the downstream verification, there is a possibility that ASPA alone cannot detect these types of hijacks when it is received from a provider to a customer. So these are essentially fake link or forged peering attacks, which I'll show in a moment. So our goal is to detect and mitigate these fake link attacks received from any direction from a provider, customer, or lateral peer. So ASPA route leak detection capability. So one clear goal here is to keep the ASPA route leak detection capability intact. We are not going to meddle with that. That is the base that is important to all of this. So we have acknowledged this problem of one little gap with ASPA verification. We try to find the up ramp on the left and find the down ramp on the right. And these are with the help of ASPAs, customer to provider authentications. ASPA is used. At the top, these two ramps may merge onto one AS. In that case, there's no issue. If these two ramps merge on two different ASs like 3 and 4, ASPA of 3 may have ASPA or 3 may not have ASPA. It doesn't matter. In either case, the following happens. 3 attests that 4 is not a provider, or 3 says that 3 has no ASPA, in which case we don't know whether 4 is a provider, customer, or lateral peer. In all those cases, if 4 is in the path, then no doubt that this path is valid. So only question is 4 faking a connection to 3? Is 4 really connected to 3? So that's the issue. So far out, somewhere else, there is a ASX, and there is a ASY, which is a customer. 1, 2, 3 are another part of the internet. And if X somewhere else can fake a link to 3, so 1 has ASPA, 2 has ASPA, 3 may or may not have ASPA. So X can send it down to Y, and the ASPA, as it stands now, would determine that it is a valid path. because 3 to 4 can be customer, provider, or lateral peer, it doesn't matter. I'm sorry, 3 to X. And in all those cases, Y would determine the path to be valid. So there is a fake link issue here. X can fake a link with 3, or X can fake a link with 1 or 2, and it can get away with it in the downstream direction, but not upstream. That is well recognized. And also, maybe 4 is not somewhere far away, 4 is in the path. However, 4 received a longer path from 1 to 2 to 3 down to 4. And 4 now fakes a link with 2. By doing that, it shortens the path and sends it to its customer. Again, it's a downward direction attack. The other alternative that the customer has through 6 is valid, but it is not able to differentiate. In fact, it sees a shorter path from 4, although it is invalid, and accepts it. So, and then a customer can also take advantage of a non-adopting ASPA. In this case, 6 can take advantage of 7 not adapting it. And so then 7 prioritizes the customer route over another route it may have received from elsewhere, and sends that to 5. So 5 is indirectly attacked by 6, although it still does come through 7. The important thing here is partial adoption. So we in partial adoption, these things can happen, and this example serves to show that if you have something else like what we are proposing, ASRA, then even in partial adoption of ASPA, if you also have ASRA, so if one in this example has both ASPA and ASRA, this can be detected by 5. So the solution is in the form of a new RPKI object, which we call Autonomous System Relationship Authorization. It allows the registration of customers and lateral peers. So either the ASPA or the ASRA must confirm a BGP peering link with the next AS in each hop in the AS path in the forward direction, in the direction of the path. For example, ASI to ASI plus 1, we will call it a fake link if ASI's ASPA and ASRA both exist and neither of them attest to a relationship with ASI plus 1. So that's the key, that is the central point of the solution. ASPA alone method its guarantee is that the AS path is feasible. ASPA plus ASRA method gives you the additional guarantee that if there is a fake link somewhere in this path, then that can be detected. So we have 4 subcategories of ASRAs. ASRA C, LP, CLP, and TICS. C is for customers, to register the customers. LP is to register all lateral peers, and ASRA CLP, in case the subject AS is not willing to disclose the customers separately as a list, they can combine lateral peers and customers into one list and not be explicit about who their customers are. They don't want to reveal. In that case, they can register them as a combined list. We won't be able to differentiate them in the algorithm, which is a bit of a disadvantage, but that can be option. For the AS. And finally, ASRA TICS. TICS is transparent IXRS, RX, and the proposal is for the TICS to declare itself as a TICS using ASRA, and then it can optionally register all its RS clients. So by doing that, the following happens. If 2 and 3 are clients of a TICS RSAS 100. What the TICS RSAS does is to register a ASRA TICS in mentioning itself, 100 in it, and it can optionally include all its RS clients. It does not have to, it can optionally include them. And then ASPA 2 and AS2 and AS3, those are the RS clients. They are peering at this RSAS. They create ASPAs and include 100 in the ASPA, in their ASPA. So we know from the TICS ASRA, in the TICS ASRA, we know that from that we know that 100 is a TICS RSAS. And by looking at the ASPAs of 2 and 3, we know that they are both pointing to 100 TICS RS. So they must be clients, and therefore they are effectively lateral peers. So right there, we know that there is a connection between 2 and 3, albeit through RSAS, but they are lateral peers in effect. So where this helps is that, so this clearly, like briefly describe the solution to you. There are detailed algorithms, and I have a bunch of slides in the backup, which we'll not go through today. The algorithms are well described there as well as in the drafts. So the algorithm basically is able to catch these fake links based on the use of both ASPAs and ASRAs. So one other side benefit of ASPA plus ASRA is that combined, they detect together more route leaks than ASPA alone in partial deployment. So this is partial deployment example, for example. And in this, one has ASPA, it may not have ASPA, that would also be fine. 2 has ASPA and ASRA, that is the key. And if two happen to leak it to 3, and then 3 passes it down to, so 3 itself is not doing ASPA, but 4 is doing it. 4 would not be able to detect it based on ASPA alone. But if we have 2 has both ASPA and ASRA, then that confirms that 3 is a lateral peer. For example, 2's ASPA says 3 is not a provider, and 2's ASRA says 3 is the lateral peer. Either through an RX, TICS RXAS or directly. We can catch both from ASRA. So in that case, we clearly see that there's a lateral peer and this path should be invalid, and 4 would be able to detect the invalid in this case. So there are benefits for early adopters. You just need the ASPA-ASRA adoption by 2 ASs, and between these 2 ASs, if other ASs don't adopt, we still would be able to detect fake links if any happen. And especially, I mean, the adopting AS, from there, if there's a fake link, that can be detected. Thank you, and I'll be happy to take questions.
This is Maria from BERT. I'd like to note that I have been turned down with the request to prepend single AS numbers in the ASPA verification, and now we are proposing a mechanism which is going to put into the routers potentially much bigger and larger and more complex databases, where I would have to look whether the feasible parts of the AS path are beating here or here or here or there, and if any one of these fits, then there is probably valid. I am seeing a lot of problems with this. I'm not against working this way, but I'm a little bit concerned that this is going to have a lot of friction.
You are what? So I'm sorry, the last sentence? Okay.
It's gonna generate a lot of friction.
Okay, thank you.
Yang Fei from Zhongguan Laboratory. When ASPA is conflict, when ASPA conflicts with ASRA, what's the results?
Okay, good question. One thing very clearly we state in the draft and make it absolutely clear that ASRA would never take any precedence over ASPA. And also we use ASRA only in the forward direction, because we are looking for possibility of ASI plus 1 faking regarding its relationship with ASI. So ASI plus 1's ASRA, we never consider that. We only consider ASI's, the preceding ASs, ASPA and ASRA. So thanks for that question. We took care of that in the draft.
Jeff Haas. I'm here to say that I think that you're going to want to allow the conflicts. Using slide 10 as your example topology, just to comment on this, a complaint I've had for a very long time about ASPA is Gao-Rexford is a business practice. It has nothing to do with correctness of the BGP protocol. The consequence is anytime you have a complex style relationship that violates Gao-Rexford, which 3 and 4 would have if they are, not ASPA peers in terms of the Gao-Rexford, but are valid BGP relationships, ASRA can model this. You therefore, if you want to allow that use case and allow for the complex behavior, are going to need the ability on a per destination basis to override that ASPA should not be enforced for a given destination for a given ASRA path. We can take up the case later, but I'm just raising it that way.
Yeah, I would like to understand the details of that. But I think we did discuss complex cases fairly well in the draft, but maybe it still requires some more thinking, and I'll be happy to discuss offline.
Thomas Schmidt. I wonder from a trust perspective, if I look at this declaration of a lateral peer, wouldn't it be necessary to have this declared by both? Because a lateral peer is a equal relation, and if 2 declares it, but 3 says no, then it actually is not valid, right?
Yeah, we are already trusting 2's ASPA. So we take 2's ASPA into consideration and we trust it fully. So true, if 2 also has ASRA and it declares 3 to be a lateral peer or no connection with 3, then we want to trust 2 about that more than we would trust 3, because 3 is potentially the one who is faking a link, not 2. So we are going in the direction of the flow of the update.
This example, 3 simply has no ASPA. It is not faking in your picture here, right? So I was just wondering, I mean, declaring an upstream provider is a one AS statement, and lateral peer I would expect it to be a 2 AS statement.
Yeah, ASPA may not adopt one situation, and if it did adopt, and if it confirms that 2 is a lateral peer, then that is even better. But we don't explicitly need that information for the verification.
Alexander Azimov. So 2 comments. First of all, I admit that there is a significant progress by introducing this special object for the transparent access. At the same time, from the operational side, it makes things significantly different from the ASPA, because in ASPA, customer is responsible for keeping its ASPA object up to date. Here happens a delegation. It's IX who should keep the object up to date for its customers. And if something happens, if it's not up to date, it will be kind of indirect responsibility. So it's kind of delegation, and it's very important to point out. Second comment is that you were correct while describing the limitations of ASPA, especially for prefixes that are received from providers. But it's also important to highlight that ASRA doesn't fully cover the problem, because it's a window for replay attacks. Not replay. It's not replaying, but to construct a path that will be valid even in ASRA world, but it will be just a artificial construction. And also getting back to IXS, it doesn't cover the scenario of selective peering inside the IX.
Yeah, I think I take the comments well. So we can, I think you and I need to talk a little bit more and discuss about the IX cases, which I think you are concerned about. In this one, I don't know if you are concerned about the RS revealing all its clients. It doesn't have to, that's optional. As long as 2 and 3 attest that the 100 is their RS, they are good. I mean, we are good. And so therefore, it doesn't have to be a full adoption on part of all the clients of an RS. Some of them adopt, that is fine. So again, like the partial deployment benefit is that ASRA might be adopted in just a handful of ASs, and they benefit for sure immediately. So it doesn't have to be just like
I'm sorry, maybe you continue offline.
Yeah.
we are running very late. So.
Hello everyone, I'm Ying Su from ZGC Lab. Today, I will introduce our new draft requirements for RPK Reliant Party. This draft aims to refresh RFC 8897. RFC 8897 provides a single reference point for RPK software requirements. It helps implementers identify RP relevant requirements across multiple specifications quickly. From the experience in developing our own RP software, we found such an entry point is very useful when building RP software architecture. However, RFC 8897 was published in 2020. Since then, the RPK ecosystem has evolved significantly. Several new specifications and updates have introduced new requirements for RP implementations. These include several new signed object types, updates to the synchronization mechanism, validation procedure updates, RTR relevant work, and new operational considerations. So the RP requirement landscape today is different from the one described in RFC 8897. The goal of this draft is not to redefine RP behavior or create another layer of RP requirements. It is to update the RP-oriented reference map provided by RFC 8897. It organizes RP-relevant specifications around the RP processing model, including repository synchronization, certificate and CRL processing, signed object validation, validated cache distribution, and new operational considerations. So the authoritative requirements remain in the individual specifications themselves. The overall structure of this draft still follow RFC 8897. Most existing areas are returned and updated, while some areas have major updates due to the changes of the RPK standard. For example, RPK repository synchronization and the signed object have the major updates due to the new repository synchronization mechanism and the new RPK signed object type. We also add two new subsections in the introduction. One describing the changes since the RFC 8897. The other one clarifying references to the active working group drafts. We also add a new area which called operational and management requirements for RPs. This slide summarizes the major technical updates. First, the RPK repository synchronization incorporates updates related to the RDP, such as same origin policy, desynchronization recovery, and the new synchronization mechanism, ERIC. Second, trust anchor has involved the new signed object TAK and trust anchor selection mechanism. Third, certificate and CRL processing has been updated according to the path validation updates and the CRL handling work. For signed object, this draft also updates the requirements for the ROA and manifest and adds the new signed object type such as ASPR, TAK, and RSC. This draft also updates the validated cache distribution mechanism with the RTR version 2 and add a new section operational consideration. We also include some active SIDROPS working group documents. These documents are included because they are directly relevant to the RP implementation, but these documents we may consider them provisional if the content or status of this document changes, the corresponding reference may be updated, replaced, or removed. Today, the modern RP software is a continuously operating security component in the production network. So operators may need visibility into repository synchronization, validation procedure, and validate output state. So this draft also includes 3 operational considerations. The first one is validated cache export. The second one is observability and diagnostics. The third one is audit trail. This capability help operators compare results, troubleshooting, and analyze RP behavior. Finally, this draft is not intended to replace the underlying specifications that RP developers must read. It is to help them identify which specifications are directly relevant to the RP implementation and helps them understand how these specifications fit together from an RP workflow perspectives. Yes, we would like to get some feedback from the working group on this document. Thank you.
Job Snyders. I will reiterate some feedback I shared on the mailing list. In the development of an RP, the development team needs to make an overview of what RFCs exist and which ones are relevant and which ones are canceled out by other RFCs. And this is a fair bit of work. I know from experience, and I think you know from your own experience. This is a fact. It takes a little bit of research what to implement to make an RP. But the specific RFC of RP requirements literally was outdated already before it got published. And I think that in trying to update that RFC, we will repeat that dynamic of it always being yesterday's news. So I do appreciate the work that has gone into like what does a modern RP look like, and I think that type of helicopter overview is valuable. But I think RFCs are not the best publication venue because of the slowness of RFC publications. So I think another way to use this work and help future developers could be to use the SIDR Ops wiki and have a page that outlines like this is the current state of the art for an RP. These are gotchas or optimizations you can think about, or tricks like, yeah, let's jointly document how our collective RP implementation experience. But yeah, specific on updating the existing RP RFC requirements documentation, I think that RFC should just be marked historic, and that would help developers more than updating it every 5 years. So, but this is my take, and thank you for the presentation.
Oh, thank you for your comment.
Okay, thank you.
Hi everyone, my name is Alex Mendel from TU Dresden, and what I'm about to present is joint work with Thies from RIPE NCC. So the research question that we kind of set out to answer was how fast does the data plane react to RPKI ROA changes? And so effectively you do this by having a trace route before the ROA change and then a couple of trace routes during and after the ROA change to figure out how the paths changed. Now, this is not entirely new. There's prior work that asks the same question, and that work usually uses RPKI beacons, so prefixes they control, and they sign the ROAs for themselves, and they flip it valid, invalid, and then run trace routes to that prefix from their vantage points. But that limits the topological coverage to the upstreams of the AS that is running the BGP, the RPKI beacon. Now, it would, of course, be better to use in the wild prefixes, because then you cover a more diverse topology, but this introduces uncontrolled behavior in that we do not know when these prefixes might flip in their validity status, or the announcements flip in their validity status. So the question is, how can we start measuring on the data plane before the RPKI ecosystem sort of reacts to a ROA change? And our answer to this is effectively run a very optimized validator, and instead of looking at the public repository, look at the CDN origin of the RIPE NCC repo and get every news a minute early compared to the rest of the internet and the RPKI ecosystem. And so by looking at that origin with the optimized validator, we then run trace routes from 300-ish globally distributed vantage points to the impacted prefix of a change for 1 hour every 3 minutes. Now, you may ask correctly, so does that work? And the answer is yes, at least for our 3-month observation period. We took a list of public validators, so run by Cloudflare, by RIPE, and a couple more from some IXs. And we compared when we observe a change versus when those validators publish or push a change. And we were at least a minute faster, and in the median, we were like 5 minutes earlier than those public validators. So good enough. Now, what did we observe? First of all, we ran our measurements for 3 months from the beginning of November 2025 until the 31st January 26. And we, in the RIPE repository, observed 25,000-ish ROA transitions that affected the VRPs. So we only are interested in changes that change the VRP. We don't care about CA resigns or valid until changes. We only care for those that can impact the validity in that moment. And of these 25,000 transitions, we have 1,493 transitions that go from or into an invalid state and that do not have another covering announcement. So these prefixes should be disconnected or connected to the internet if they flip into or out of invalid. And yeah, we measured how fast they appear and disappear. So this is from an invalid state into a non-invalid state, so either valid or not found. The graphs are separated into upstream number of upstreams, and this is for the AS originating the prefix that is going valid. We derived this number of upstreams from RIPE risk data, so we may be overestimating, or we're probably overestimating the number of single upstream networks, but it is good enough for this comparison. And for single home networks, announcing, again, the prefix that has changed its validity status, the median time is 12 minutes until 50% of our vantage points are able to reach that prefix. And for the multi-homed case, the median time goes to 9 minutes. So you're quicker if you have multiple upstreams, or if the originator has multiple upstreams. And we can look at the same thing in the other direction. So going from a non-invalid state to a invalid, the times increase quite drastically. For if the announcing AS is single-homed, the median time until 50% of our nodes are only able to reach the prefix is 30 minutes. And for multi-homed systems, this time increases to 42 minutes. Also note, we only ran the trace routes for an hour. So the big blob at the multiple upstreams 60-minute is not because everybody withdraws at that point, but because I stopped measuring at that point. Another fun thing that this data has is that I can look at how fast large networks withdraw invalid routes or sort of stop routing them. And this graph shows the last time a probe that had observed one of these networks in its trace routes stops seeing that network in its trace routes when going from a not invalid state to an invalid state. And we can see on the left sort of the 15 to 20 minute range is probably what we expect networks running 10-minute polling intervals on the validators to look like, because there's a bit of head start that our method has, and then there's sort of, yeah, somewhere around the 10-minute reload time. And then the other providers are probably running less often polling intervals. Now, what do these results mean for you? One thing is that deploying RPKI or setting a ROA during a hijack might not be quick enough. So for example, the sort of well-known Route 53 hijack a couple of years back only lasted for roughly 2 hours. And in our data, after 42 minutes, 50% of the vantage points were still able to reach these invalid prefixes. But there's also an easy solution to this: create ROAs before there's a hijack happening, so you don't have to rush this much. And secondly, have validators refetch in shorter intervals, so 10 minutes or less is probably a great call. Or your RPs, so this is what the validator is for. Okay.
Thank you.
Thank you.
Jeff, there is one question.
Jeff has one question, slide 12.
Yes.
So we're seeing, using Aurelion as the example and Cogent as well, that the stretch on this is very long. I would expect this to be a tight blob. Have you formulated any theories why that?
Yes. The blobs for the ones that are slower is actually they're benefiting from the quicker networks. So if one of the quick networks is right in front of the announcing AS, announcing the invalid, and they quickly turn off the announcement, and that is the last announcement for this prefix, then all the others get the same quick timing because they get a withdrawn route and also withdraw the route. So essentially, if we have Cogent, NTT, the origin AS announcing the invalid, and NTT quickly withdraws that announcement following the invalidation, this quick withdrawal also happens for Cogent, and that's why they have a blob at the same area that the quicker ones exist. Yeah.
Okay, to summarize, thing number one, the closer to the core you are, the better you're going to have results. The second problem is this is a last man standing problem. BGP normally has that. And this just happens to be showing that the last man standing problem is actually far worse.
Yes,
than we should.
Yeah. So that's quite correct. This was pretty clear that this would look somewhat like this, both with this being fast, this being slower, because that's just what BGP does. It looks for connectivity. So establishing connectivity is quick. Losing it takes a bit. RPKI just increases this in an order of magnitude.
A quick one, Joe.
I just want to say thank you for this research. I think it is really awesome how you managed to convey the dynamics of the system. So thank you so much for coming here and sharing this study with us.
Thank you.
Thank you for being.
Thank you. Yes. We have 7 minutes left, so we're going to try and squeeze one more presentation in. Sorry if there isn't time at the end for questions. We'll see.
Hey, am I audible? Hi, everyone. So I see the oldest slide to be uploaded, no problem. I'll just brief it out for everyone. It's basically RPKI over the QUIC protocol. For my co-authors, I will be going through this draft and my implementation. Okay, so before we dive in deeper as to how we would like QUIC to help in RPKI, a couple of beneficial points that we see is QUIC has the inbuilt security mechanism, the TLS encryption, for which, like unlike TCP, like where we need to have an enhanced separate support for security like TCP/AO or MD5, we don't need any such extra security mechanism here. Second is basically the restoration and the establishment time that is pretty fast. We don't have the blackout time over here really. Like when the servers are getting restored, we have the validation done pretty fast. The next one would be here we maintain a couple of streams within one connection, which means that we have control on the flow of packets for each of the streams, and we have a proper control of them. And quick connection ID allows session survival when the client's network address changes. So these are few of the benefits that we can take a look for quick. Coming to the establishment now, the thing is we need to share a particular identity, RTRO quick, to the cache that we want to support RPK over quick. So basically the router should be acting as the client while the cache must be the server. Along with that, so there is we don't get the early data implementations over here. We should not be allowing that. Without proper setup, we should not be sending any application data towards the cache. Similarly, for the termination, we follow the RFC for quick as defined in RFC 9000, and for the idle timeout, we definitely maintain that a pretty high value, so that if we do not receive any packets for a given time, we do not terminate the session. Okay, so couple of PDUs, we can distinguish them between we can majorly broaden the two categories as data packets or control packets, and ideally we can punch everything in a bidirectional channel. As I already mentioned, there will be a couple of streams within one connection. It can be bidirectional, it can be unidirectional. We can punch in all the PDUs in a bidirectional stream if we want. But the benefit, or for better efficiency, we can use unidirection channel for the data packets, because it's going to flow from just the cache server towards the router. Whereas the control channels or packets, the control packets will be going by the control channel, which needs to be bidirectional and need to be brought up soon after the connection establishment. Right? So there are two ways for data channel which we can operate in. So we can either spin unidirectional channels soon, before we send the cache response from the cache server, or we can spin up bidirectional channels accordingly. That we will take a look in the following slides. All right, so if we go for unidirectional channels for data packets, ideally that should be spinned before we send a cache response PDU towards the router from the cache. So after we get a request for a serial or a reset query, while we send the cache response, we should be sure of spinning the unidirectional channels for the data packets, right? And
you have 1 minute left if you want to
sure.
maybe.
And before so that's basically to fasten up. I'll just keep elaborating on it. So we can go for the unidirectional channel, or it can be bidirectional channels. For bidirectional channels, ideally we spin the bidirectional channel before sending the serial or the reset query. This termination happens once, the session can be terminated after receiving this end of data PDU from the cache server, or it can be kept as per requirement. So 4 data channels for 4 different types of data packets: V4, V6 ROAs, or router key PDU, or ASPA PDU. So yeah, I did pretty fast, elaboration of it. So the main thing is that we should be sending a flag RTRO quick towards cache to resemble that we want to support RPK over quick.
Right, I'm sorry, I apologize, but the time is over. I would suggest next time to go on the why, not on the how we do the quick thingy. If you ask for 5 minutes, you have 5 minutes. I mean, not 12 slides. I'm sorry. So we take it to the list to continue the discussion on quick, okay? And time is over. So
Sure.
we'll meet in San Francisco. Thank you for all.
So thank you all. We have less than a minute left in the whole session. So thank you very much and have a good rest of your meeting.